1/3 x cubed plus 1/4 y to the 4th dot dr. But the integral of a conservative vector field, right, over a loop is 0. Apply the fundamental theorem of calculus. Whatever floats your boat. The point is we get 2 pi. Right? Now, so this, let me define a region. So let's say that this is the unit circle, x squared plus y squared equal to 1. And then we can just let the region be the exterior to that. So it's sometimes called an exterior annulus. In the sense that the outer circle's at infinity. I can be more specific here. It's, it's just, it's x comma y such that x squared plus y squared is greater than or equal to 1. So this is the region that I'm talking about. F is locally conservative on that region. Why do I say that? Because, in other words, the curl of F, the z component of that, right? Well, fine. Calling this P, calling this Q, we have partial Q partial X is equal to partial P partial Y, because of the calculations we've already done today show that. The new piece that I added, the x squared and the y cubed, don't change that. Those differentiate to 0 under the y and x derivatives I'm talking about here. So it's locally conservative on this region R, but it's not conservative.
So it's conservative everywhere except at the origin?
Again, conservative is something that applies to a region. So I would say it's locally conservative everywhere, but it's not conservative on this exterior annulus, because there's an integral around a loop which gives us 2 pi. In fact, any loop which encircles the origin is going to give us 2 pi for this vector field. If, on the other hand, you had a loop like this here, then the integral, let's say L, the integral of L of f dot dr would be 0 out there. Because of Green's theorem. I can apply Green's theorem to this loop, right? And Green's theorem in that loop is what? It's p dx plus q dy, right? Over the boundary, which I've called L, right? Suppose that's the boundary of B. Well, that's the integral over B of partial q partial x minus partial p partial y, right? Which I'm telling you is 0. So any loop for this vector field which does not enclose the unit circle, if it doesn't enclose that unit circle, then we're out. Now the unit circle is just something I made up, right? You could choose a circle of any radius here, it would be the same problem. The real issue is, do you encircle the origin? If you want to work with what's called the punctured plane, just throw out that one point at the origin, the same story. So anyway, it's interesting. There's an interesting interplay between Green's theorem and conservative vector fields, right? There's a lot of interconnections here. We can understand them more deeply like this. This brings us to, I've got a couple pages again on two-dimensional electrostatics. I don't feel inspired to talk to you guys about that today, so I'm not going to. It's interesting, and I should talk about it someday, but just maybe not today. So our next topic is surface integrals. So we talked about line integrals, and I've given you most of the main theorems about line integrals. Next up, surface integrals. What is a surface integral? So the idea of a surface integral is as follows. So you're given, what are you given? Oriented surface. I'll call it S, all right? Which means that you have a normal to S. You have a sense of which direction's up, or at least out for your surface. And you're also given a vector field. And, you know, F. If you like, we could do PQR, but I don't usually do that much here. All right. Your goal, you calculate. So that's the input. In, out. The integral, I'll write two integrals. It's kind of like an area integral. This is the surface integral of f dot ds. So this is our notation for the surface integral. This is a measure of what's called the flux of the vector field through the surface. And I'll just give you the definition. It's going to be the integral over the domain of the parameterization of the surface of f of x of u comma v dotted with partial x, partial u cross partial x, partial v, du dv, where this x is a mapping from the domain, which is some subset of R2, to your surface, which is some subset of R3. Here, x of uv is equal to x of uv, little x of uv, little y of uv, little z of uv. This is a parameterization or patch of S. So to calculate a surface integral, we must parameterize the surface, evaluate the vector field at the surface, at the parameterization, and take the dot product with the normal vector field, which is induced from the parameterization. That's how we actually calculate it. Now, there's a more basic geometric way of thinking about this. What's your question, Sam?
I was just wondering, why did you write f dot ds rather than f dot dn?
ds is the infinitesimal surface area element. Well, vector surface area element, I should say.
The line integrals, like we would call the curve C, but then we said f dot dr, not f dot.
I don't know. It's just notation. Depends on the book you read. Some people will use the integral of f. I've seen this other places, dA vector, like that. And this doesn't have to be s. It could be, you know, whatever, Bob.
Right, yeah.
I wouldn't write dBob there. This s and that s are not connected. So like s 42. I mean, whatever. I mean, it's not the same s. Okay. So this right here, guys. This right here, guys, is what we call ds vector. This is the vector infinitesimal area element. I think we have time for one good example here. So we'll let f equal to ABC, right? And we'll look at s equal to, I'll keep it pretty simple here. Let's let s equal to the x, y, z such that x plus y I'll make it really simple. Z equals to 3 and 0 less than or equal to x less than or equal to 0 less than or equal to x comma y less than or equal to 2. It's a pretty simple one. So what's my parameterization? So here's my surface S, right? So I think we can use x and y as parameters, right? UV is what? It's u, it's v, it's 3. So what's partial x, partial u? What's partial x, partial v? X hat and y hat, right? So what's my ds then? It's x hat cross y hat, dx dy. So in other words, yeah, it's z hat times dx dy. And so put the pieces together. I'll do it over here. The integral of f dot ds over the surface S is the integral of, and this one's kind of boring, ABC, right? Dotted with z hat dx dy, right? Now this is the integral from 0 to 2, the integral from 0 to 2, right? Because you notice my d is x comma, well, it's u comma v such that what? So I'm sorry, guys. I didn't mean to put dx and dy here. I meant to put what? I meant to put du dv. Now, you see, you could put, I mean, we could be writing, you could reasonably, I'm just trying to pull it back to the definition, at least to start with, yeah? So sorry about that. What I had written wasn't wrong. It just, again, wasn't right. And so this is just the c times the integral from 0 to 2, integral from 0 to 2 of du dv, which of course is 4 times c. What is this really? This is equal to the area of S, right, and times z hat dotted with ABC. This is the flux of ABC through S. In physics, if you deal with constant vector fields, you can calculate flux by just multiplying the magnitude times the area if they're directly cutting through. But generally speaking, you only want to cut the part of the vector field which is actually cutting through your area, so that's why we need the dot product. Here, the A and the B part, they're tangent to the surface, whereas the C part actually cuts through, and that's why we have C times 4 for the flux here. Anyway, I will do many more examples of these. So many, we'll get tired of it. Thanks, guys.